Hi everyone, this is Miss Silverman and I'm back. I'm on page 164 of our math physics book, and I'm continuing to explain what we kind of see in our ripple tank when we are analyzing kind of the funny nature of two-dimensional waves, specifically water waves in this instant, although it applies to other types of waves from sound to light, which we'll study in the future. We're still talking about the second of 5 properties of waves. We talked about linear propagation, and we're now talking about a reflection of waves off different types of barriers. Okay, so we're on number 7 now, and we're going to see what happens when straight waves, and I'm going to say straight wave fronts specifically, are reflecting off of a parabolic barrier. So we have these straight wave fronts coming in. Of course, their ray looks like that. And the question is, what do they look like afterward? On the previous page, let me see if I can find that. On the previous page, we said for any straight barrier, if we have a straight wavefront coming in, we're going to get a straight wavefront going out. And that's what we saw in these cases, right? In the last one, we saw that a circular wavefront hitting a straight barrier is going to produce a larger circular wavefront coming out. So my question is, well, what will happen to these straight wavefronts? Okay. Some potential options are that if we have, this is the after image. Okay. So some potential options are we have this kind of curved parabolic thing, and we'll get straight wavefronts back out. Another option is maybe we could get circular waves or circular wave fronts back out. Or, I don't know, maybe they do something crazy. Maybe the waves somehow like go down. I don't know. So let's check it out. And you feel free to draw this kind of right on this image here. I think I'm going to try to draw a little larger just so it's clear for everybody. So here's my parabolic barrier, and I have these straight plane waves, or sorry, these straight wavefronts coming in, also called plane waves, coming in towards our curved parabolic barrier. What's going to happen? Well, again, I think I'm going to invite our little surfer dudes to help us understand wave behavior. So this little surfer dude's A, B, C, D, and E. So they're going to be coming straight, right? Straight in, just like that. And again, to help set our stage, we're going to find the tangent to the curve, and we're going to draw a reference line. Remember, our reference line is always normal to the barrier. Because we need to find normal to a curved surface, I'm finding the tangent line. Now, I find my angle of incidence. That's between the incident ray of A, which is right here. That's the incident ray. And then I'm going to draw my reflected ray, which is kind of like going out here somehow. Same thing with B. This one's still a little curved. I'm going to draw it. This normal line's kind of like that. Will probably reflect somewhat like that. This is going to bounce straight off. This one probably kind of reflect over here. This one, whew, is going to go way over there. Okay. Now we notice a couple things. we notice that the path of all these little surfer dudes cross. The question is, do they all cross at the same time? And the answer is yes. Now, if we look at the path of little surfer dude E from here to here, the length of this segment plus this segment is going to be equal to the length of this segment and this segment. Be a little hard to see here, but that's okay. And they're all moving, these little surfer dudes are all moving the same speed because again, well, they're all moving the same speed because well, they're in the same medium, water. So that means they all reach the same point at the same time. They reach the same point. Now that's interesting. If they all hit the same point at the same time, that acts like a point source. When we know what happens when we have a point source, we create circular waves. Just like that. So this is our before image. And we have all this stuff to show what happens in our after image. So we start to notice that when we have these straight wavefronts coming into a parabolic curved barrier, out comes these circular wavefronts. Now this point source is in a special location because it is at the focus point of our parabola. Parabolas are pretty special shapes. That's why our satellite dishes are parabolic. So, some fun facts. So again, kind of all energy collects at one point. And that is the focal point of our parabolic barrier. And that acts as a point source. And we propagate outward as circular wavefronts. Okay. Now we see these parabolic dishes not just in satellites, we see them in lenses, other optical instruments, eyeglasses, contact lenses, also other satellite dishes, deep space satellite dishes. So it's a pretty special shape. So I drew this image right here for you. So now we can say for any parabolic barrier, if we have a straight wave coming in, out comes, and I'm going to say instead of a straight wave, I'm going to say a wave front. It's a two-dimensional wave. Out comes a circular wave front. So now let's think about circular waves reflecting off of a parabolic barrier. We're on part 8 now. So here's our before image. Again, if we have circular waves, we need a point source. And the question is, when it hits this barrier, well, are we going to get circular waves back out? Are we going to get these kind of more linear wave fronts out? And the answer is we actually get linear wave fronts coming out. And I'm not going to draw kind of any more complicated images like this, but really it's kind of the reverse of this whole process. Okay, that's why we get these straight wave fronts coming back out. So now we can reason for any parabolic barrier, if we have a circular wave front coming in, we get linear wave fronts coming out. Okay. Before we move on to 9, we're just going to summarize some of what we learned on page 160. Sorry, we're on page 163 right now. Forgive me. I'm going to summarize what we learned on page 164. So The first wave property we learned about was linear propagation. All waves travel in straight lines. And then we also just learned about reflection. And remember, reflection is that all waves can bounce off matter. And we have the law of reflection. The law of reflection, remember, that states that our incidence angle, or the angle created between our incidence ray and our reference line, is equal to our reflected angle, which is the angle between our reference line and our reflected ray. Excellent. And we also found out this kind of beautiful potpourri of all these different quirky behaviors when different waves hit different types of barriers at different angles. So number 9, we're going to start to apply the wave equation to learn about a third wave property. So if you recall, the wave equation is V, which is velocity, speed with a given direction of a wave, equals the frequency of a wave. Remember, frequency is the number of waves we see per unit time, multiplied by the wavelength, or the distance from crest to crest or trough to trough of a wave. All right. Now, let's think about this. Let's apply this equation to what we saw in our Ripple tank lab, okay? Now, let's imagine that I'm just trying to generate these initial waves that we made when we just vibrated our wooden dowel back and forth in our Ripple tank. And let's say that I'm just very slowly vibrating my wooden dowel back and forth in my Ripple tank. That's probably going to create these linear wavefronts that look something like that. On the other hand, let's say I try this experiment again and I start to vibrate my dowel much faster. Well, all of a sudden, my linear wavefronts look a little more squished. Okay. We notice here that we have some really large wavelengths. And we have much smaller wavelengths here. If we're trying to apply this to our equation, okay, let's think about what happens. We know V equals frequency times lambda. These waves, or wavefronts, are all moving at some velocity in water. And that's going to equal a really large wavelength. And if this is really large, our frequency has to be pretty small. I'll make it even smaller. Very low frequency. Now, let's try to apply this equation over here. Well, what's going to happen to my speed? Both of these are in water. And if they're in the same material, we're going to have the same speed. So these speeds are the same. This wavefront is going at one speed. This wavefront is going at the same speed. The difference is the wavelengths, or the distance between crest to crest, is very small. Therefore, the frequency is going to be really big, a very high frequency. We're going to see lots of crests, lots of wavefronts per unit time, versus here, in that same amount of time, we're really only going to see a couple. We can just summarize what we found by stating that frequency and lambda, or wavelength, are inversely related. Okay. Perfect. Number 10, we're going to think about medium. Again, that medium is the material that waves are propagating through. And when we were talking about a Ripple tank, our main medium was water. Okay. If we want to try to change the medium in water, what's kind of interesting, and this is kind of a little easy cheat, instead of like making a wave move from maybe water to molasses, what we can instead do, and I hope you can see this here, is that changing the depth of just water actually like changes the medium. And what we mean by that is that kind of change, it's almost like fake changing water, because water depth makes it behave kind of like a different substance, at least in the eyes of a wave. So I keep saying that if we have the same medium, well, then we're going to have the same velocity. But now if we change the medium, or if we start deep and go a little shallower, that means we're going to change the speed or velocity of our waves. Okay. Now, based on my wave equation, if I change my velocity, okay, I'm going to have to either change my frequency or my wavelength. So I can say I'm going to change my wavelength. And I want to do a little demo for you, but I need some string. 1 second. Well, there's this lovely demo that hopefully we'll do in class for you, but I don't know if I can do it in this video tutorial right now. If you change the wavelength of a wave, you're actually going to induce a change in amplitude. Remember, if we're talking about amplitude on a transverse wave, because it's a little easier to see, we're thinking about the height or the distance from equilibrium to the crest or trough of a wave, right? Now, imagine that this transverse wave was a piece of string. And imagine I pulled this string out. What do you think is going to happen? Well, of course, the length of the string is going to stay constant. What you see instead is something that's going to look a little more like this, right? So it's all squished together, and I'm going to pull it out. What do you notice? Well, we definitely noticed a change in wavelength. This used to be our wavelength. Now this is our new wavelength. You can see it's much larger. Now let's look at our amplitude. This amplitude was fairly large, but now this amplitude is much smaller. It's a very small a. And I hope this is a nice demonstration for you that, again, if you change the wavelength of something, you're going to induce a change in amplitude. And all that's created by changing the medium or material that a wave moves through, thus changing the velocity of it. Okay. Now, before we get to number 11, I want to jump to page 164. I think this is going to help us understand this. Let's think about a wave approaching a shore. Okay. Here is kind of the beach. Here's a little palm tree. Right? That's what a palm tree definitely looks like. And here's an umbrella. Right? There's like a little towel. And we got this nice sandy beach. And here's the water. Okay. Now, the water depth is constant here. So let me try to draw this a little better. So our waves are not going to change wavelength. They're not going to change frequency. They're not going to change amplitude when they're at the same depth. However, you can see when we start to approach shore, all of a sudden, the depth starts to decrease, it starts to change. Now, we just said before that when we change the depth of water, right here, when we change the depth of water, it's almost like we're changing the medium, okay? Now, when we change the velocity, when we change the depth, that's going to change the velocity of the wave, okay? And let's think about just our own knowledge before we get into physics of what we see happens to waves. We start to see something kind of like this. The waves suddenly start to get higher and higher. they start to get a little more squished together instead of maybe the more calm ocean beyond the shore. And then they crash onto the shore. Okay. Well, why is this the case? Okay. We'll try to answer that here. Say we have, again, we're at our ripple tank, and let's say this side is deep. You've got deep side. And let's say that this is our glass pane we put into our ripple tank. So this part is shallow, okay? Say this is glass right here. Let me try to draw these a little better. Remember, they'll have the same wavelength, so the distance between these linear wavefronts should be kind of all the same. And again, if we draw a ray, it's coming like that at a right angle to our wavefronts. Now, when it hits a shallower area, all of a sudden, the velocity starts to decrease and they start to slow. What we're going to see is, instead of the waves traveling at the same speed, this is if they were traveling at the same speed, these little kind of dotted lines, instead of doing that, we suddenly see a slight slowing down, okay? Something more like this. Again, we need to draw our ray such that, I didn't draw it very well, it's at a right angle to our wavefronts. So you can see that literally the direction of motion of our waves kind of got kinked a little. We notice here that, I'll write it over here, when we slow down a wave, we change its direction. I said that all waves travel, and that doesn't have an apostrophe. I said that all waves travel in straight lines via linear propagation. However, we can start to bend the waves or change the direction of waves by changing either the depth of water or the material it's going into. Right. To remember this is kind of nice. When something is shallow with an S, the wave slows, also with an S. Now we talked about the velocity, shallower depth slows a wave. Now, what happens to its wavelength? What happens to its amplitude? Well, it gets shorter, okay? The wavelength gets squished. Just like we saw on our waves crashing to the shore here. However, even though our wavelength decreased or our wavelength got smaller, that certainly doesn't mean our amplitude got shorter. No, our amplitude got bigger. Okay. Remember this kind of like thought, this little like kind of hypothetical rope demo? This is a piece of string here and I pull it out. That wavelength gets smaller, but if I were to smush it together again, its wavelength would get smaller, but its amplitude would get bigger. That's the same thing with our kind of water wave crashing against a shore. Let me see that, make sure you can see. Yeah, so here's what I'm talking about right here. Here's that little kind of hypothetical string demo, and here's our water wave. Our water wave's getting into a shallower depth right here. It starts to slow down. And when it slows down, so it's like this, when it slows down, its wavelength becomes shorter, but its amplitude gets bigger, therefore creating bigger waves. Now the question is, why do the waves start to fall over themselves? Why do they crash? Okay. Well, the velocity up here, yes, it's slower than it was over here, but the velocity of the wave up here is actually different than the water down here. And the water down here, there's a lot of friction between the water and whatever kind of gravel. So it's almost as if the bottom of the wave had a different velocity than the top of the wave. Now this isn't for all waves, this is just for water waves specifically. It's almost like if you were running up to shore. Now imagine you're on the beach, okay? And you ran into the water. And first your feet hit the water and then your torso hit the water. Well, if you ran in at full speed, your feet would hit the water and they'd slow down because the water is pushing against you. But your torso, your arms, your head would still be traveling really fast and you would fall over yourself. The waves here almost fall over themselves as well because of the bottom being slowed down by friction here. That's what happens to these water waves as they hit the shore. And that's why we like to surf on them. Okay. So that concludes page 163, and I'll make a final video for the rest of page 164. Oh, you know what? Actually, before we do that, let me add one more thing to page 164. One more thing, and then we'll wrap up this video. We're going to add a third property to our list of properties. So we just talked about something called refraction. And waves can actually bend, and that's because they change velocity. And that happens when they move through different media. So when they move from one medium, maybe like air, to a different medium, like water. Or from one medium, shallow water, to deeper water. Okay, so that concludes this video.